we are going to start and finish talking about simple machines, and then start talking about rotational motion and angular momentum. We're not going to get to angular momentum today, but rotational motion. So start with the cheater bar. Now, obviously, I was once young like you. When I was in high school, I worked at the farm and then the dairy. And so as a freshman, little 13-year-old, 130-pound, 5'6" dude, they didn't let me do much. When we were harvesting the corn, they were out there running, choppers to chop the corn and dumping it into these big wagons and then going and dumping that in the silo. Right out here, you guys are probably somewhat familiar with the process. So my job was to stay in the shop, and when equipment broke down, I helped to repair the equipment. And of course, what breaks down the most? You puncture tires on those wagons a lot. And so we're doing a lot of changing tires. And getting the lug nuts off of the wagons is a real chore because they've been rusted into place. And so you put your breaker bar on. And so in this picture, you can see right here, that's the breaker bar. It doesn't ratchet, so you don't have to worry about breaking your ratchet mechanism. And, I'd sit there and pull on it. I couldn't move it. And so we have this thing here that we call a cheater bar that we'd put on the end. And then I could jump up and hang on the end of it, and one of two things happen. Either it breaks, the socket, or it comes loose. And either way is not bad because, Snap-on tools, free lifetime replacement. So if you break the socket, no big deal. Why did we use this cheater bar? Yeah. Okay. I had multiple people's hands up. One person spoke too softly for me to hear, so I'm gonna go with Aaron.
So you have the same force but a greater radius, so it increases the torque.
Perfect answer. I apply the same force. I can't. I was a little kid, and my upward force, the strength of the biceps wasn't there, so it would have been the weight was the biggest force I could apply. I could apply that same force as I would if I was jumping up and down on it, but it's a bigger radius. So that same force for bigger radius gives it a bigger torque. And torque is the rotational equivalent to force. The bigger torque, the more likely I'm going to be able to break that thing loose and unscrew it. And so the cheater bar is our first example of a simple machine. Notice it's simple. It's not, doesn't have a motor in it or anything like that. It's a simple machine that made it so I could do something that I couldn't normally do. In this case, it allowed me to apply a bigger torque. So usually we talk about simple machines in terms of force, but you can talk about both in terms of force or torque depending on the machine. A simple machine allows you to apply a larger force or a larger torque. But of course, you can't get something for nothing. So if I'm doing work, right, if I pull this bar down, so this bar moves a distance d, that's almost a d, a distance d, then I will have done work. I'll have the force I apply times the distance parallel. And for my application here, let's just assume that the force and distance are parallel. So I've done a force applied, which I better draw the force applied. And that bar has moved the distance d. If I had put my same force applied down here, I wouldn't have been able to move it, but out there I was. How much motion do I have if I had had my force down there? For the same angular rotation, how does the distance actually move down compared? It's much smaller. And so if I actually was able to make it go out here, I would have had to have a much bigger force, but I would have had a smaller distance. So in the end, the work would have been the same. A simple machine can never do more work than you put into it. It can do less if it's inefficient, but it can't do more. So the best case scenario is that the work that you get out of the machine is the same as the work you put in. So you're not getting something for nothing, but you're multiplying the force and dividing the distance. So now our first clicker question. How does a cheater bar help remove a stuck nut? Okay, about 5 more seconds. Yes, Diamond, I have an answer for you. All right. 14, 10, that's a 10, and 27. Now, in case you're wondering with that comment, I don't have it so it shows me what you answer. I just see when a student answers, and if they answer over and over, the color keeps changing, so I see that they're answering multiple times. And it just takes the last one you enter, so it's no big deal. All right. We have a slight majority. So Felicia Christie randomly came up again. Can you give us your answer and your reasoning? I don't have, you guys aren't sending the sound right now. You need to turn the mic on. We still don't have the mic on from Southwestern. There we go. Okay, now that the mic's on, Felicia, can you tell us what you answered and your reasoning? Okay. And what was your reasoning? Oh, just guessed. Okay. Okay. So just guessing. Well, it turned out that the guess wasn't right, but if you just guess, that makes sense. Somebody else want to give your reason, specifically somebody else want to give a reason. Let's stay with Southwestern since we have their sound on. Anyone? Bueller. Okay, I heard somebody say C. Why'd you say C?
Well, I said C because it increases the length of the arm, which allows the person to put in less force in order to increase torque. So.
Okay, that's perfect. Okay. The cheater bar allows you to take off that nut because it allows you to put in a bigger torque for the same amount of force. It's not increasing the force you're applying, and it's not changing the angle necessarily. Now, of course, the smart person is going to have their force perpendicular to that bar as much as possible because you had that sine theta. If sine theta is equal to 1, you're going to get maximal torque for the force. But the cheater bar isn't changing the angle necessarily, and you can always control that. But it increases the torque you get for the same force because you increase the length of the lever arm. The lever arm is actually, usually they say R perpendicular. The distance perpendicular from the point where the torque is acting out to where the force is acting. That's what the lever arm is. Okay, so that breaker bar with the cheater bar on it was an example of a simple machine, right? The breaker bar itself is also a simple machine. It gives me a lot more torque than if I just put my hand on that nut and tried to rotate it, right? A lot more. The ramp is probably the simplest of our simple machines. you're moving. Let's say it's move-in day at school. And so you bring all of your belongings in the back of your car. Well, your car you don't use a ramp for, but in the back of a pickup. And you've got something like, a big sofa. And you want to get that sofa from the back of the car or the pickup to the ground. The easiest way to do it, if you're doing it by yourself, sofa is a bad example by yourself. Nobody carries sofas around by themselves, right? Let's go with the refrigerator. You got a refrigerator, you got to get down. This ramp, we all know, is going to make it easier than if you just tried to pick that refrigerator up and carry it and set it down. And the question, of course, the physics of it, why is it going to be easier to manage a refrigerator going up or down a ramp than it is to just bear hug it and pick it up? Okay, one of them is obviously it's hard to bear hug a refrigerator. No, it's got arms like that. But if it was something you could pick up, why is it easier using the ramp? Okay, this picture here. Suppose there was someone in that wheelchair. Why is it easier to take the wheelchair up the ramp than to just lift that wheelchair up and set it in there with the person in it?
Because you're reducing the amount of, you're spreading out like the vertical effort over a horizontal plane.
Okay, that is one very good way of describing it. You are spreading out the vertical force over horizontal distance. It's Jordan has.
Is it the effect of gravity is less like because you have the sign of gravity?
Okay, Jordan went with an equation. He said that the gravity, you're not directly opposing gravity now, you're opposing just part of it. He said sine of the angle. And that's actually the key in physics terms for describing it. And it goes with what Colton said. It's really the same idea, but putting it into equations. So if we look at the forces, so let's just now look at this wheelchair. The forces act on the wheelchair. Let's assume no friction to make life easy. What forces are acting on the wheelchair? Gila, what's one force that's acting on the wheelchair here?
Other than friction.
Okay, we're ignoring friction. So force of gravity. In what direction is that point? Down. Okay, so I'm going to show that force of gravity. There's one force. What's another force, Hannah?
Force normal.
Force normal. In what direction does that point?
Opposite of force gravity.
Not opposite of the force of gravity. That's a very important thing that is very commonly mistaken. Your sister wants to correct you. Rachel.
It's perpendicular to the surface.
Okay, perpendicular in 2 dimensions, perpendicular is the right word. In 3 dimensions, normal is the word. So it's in the direction normal to the surface, the direction coming out of the surface. So the normal force is at an angle like that. And remember, we had this question before. It was asked by Colton. Why is it not just, opposite gravity? Because the normal force is the force to keep something from going through the surface. So it's coming out of the surface to keep something from entering. It's not just opposing gravity. So we have those forces acting on the wheelchair, and then we have the force of the person pushing, which I'm going to make the force of the person pushing, I'll call it force applied, parallel to the ramp. That is your best angle if you want to minimize the amount of force you have to use. So that's why I put it that angle. So now if we look at these forces, if I want to make this thing move, I'm going to have a force applied. Well, to get it to start moving, my force applied is going to have to be a little bit bigger than the force down the ramp. And then once I get to start moving, then I can just have it equal to the force down the ramp. So when we do these, we just say, okay, to get this thing going, essentially I have to get some little iota above 0, so we'll just say it's 0. So we define our directions. X direction down the ramp, Y direction normal to it. Always have to determine, why did I choose those directions? Reason number 1 was if you have an acceleration, make sure you have your coordinate directions so that your acceleration is parallel to one of the coordinate directions. Now, in this case, realistically, I'm not having any acceleration because I'm saying, okay, I'm just going to push it hard enough to have the net force 0, which means no acceleration. So then I go to my next reason. My next reason is going to be the one that makes the problem the easiest, the one that has the most forces already resolved. And so with this selection, the force applied is all in the minus x direction, and the force normal is all in the plus y direction. So I have two of them already resolved into components. So that's why I chose that set of directions. You could have chosen other directions, but that was the one to make it the easiest. Now, to finish off, I'm actually going to redraw my free body diagram down here. Force of gravity is equal to mg. The force normal, we do not have some regular expression for the force normal. It's just whatever's necessary. And then we have the force applied. Now, I defined my directions, but you know what? It turns out that I can actually solve this problem without even using my direction definitions, because we learned how to add vectors. And this only has 3 vectors, which makes a triangle. So I'm going to apply Newton's second law, which says sum of the force vectors is equal to mass times acceleration vector, which I said is going to be 0 for the case, you just have to go a smidge over 0, and then you just keep it at 0 and it keeps moving. So I just add these together. We had this on a test question. How do you add vectors? Tip to tail. So I have to add these tip to tail. Now my lengths, of course, are fairly random. I just put those on. But when I add them up, it's actually going to have to work out correctly. So I'm going to have my force of gravity goes like this. My force applied goes like this. My force normal goes like that. So here's force of gravity. Here's force applied. And here's force normal. Where's the right angle in this triangle? It's hard to tell because, of course, I drew this freehand and it's not a quality drawing. Okay, it's between the force normal and force applied, which wasn't super obvious there either, but my x and y kind of made it obvious. And you have to know what your angle is for this to be any good. So there's my angle theta between horizontal and the ramp. That has to correlate to one of the angles in this picture. Now I could put that it's this angle, but that's not inside of my triangle. So which angle inside of my triangle is theta? It's the angle up here at the apex. How do you come up with that? Well, with this triangle, you could say, if this is theta, then this is 90 minus theta. So clearly that's not theta. The other one's 90. Some of the interior angles of a triangle is 180 degrees. So 180 degrees minus the right angle 90 minus parenthesis 90 minus theta equals theta. So there's ways to get there. Now that I have this, I am trying to relate the force I have to apply to the force of gravity. Which side of my right triangle is the force applied? And which side is the force of gravity? So that means if I can find a trigonometric function that relates opposite and a hypotenuse, conveniently enough sine, then I know that sine of theta is equal to the opposite, force applied, over the hypotenuse, force of gravity. Therefore, the force applied is equal to the force of gravity times sine of theta, which brings us exactly back to what Jordan said initially. The amount of force you have to apply is the force of gravity times sine of theta. If theta is 0 degrees, which corresponds to the ramp being horizontal, how much force do you have to apply to overcome gravity? 0. But on the other hand, you're never raising it up. And if theta is 90 degrees, then sine theta is 1, and you're just lifting. Somewhere in between, your sine theta is in between, the force you have to apply is less than the force of gravity. so it's easier to move it, to push it. So that is our simplest machine. And now I believe we have a clicker question on it. Yup. So what is the purpose of a simple machine? And it's open for answers. Okay, about 5 more seconds. Okay, so we had 40 people that said it allows you excuse me, to apply force larger than distance, 10 that said it allows you to apply a larger force over the same distance, and 6 that allows you to apply a larger force over a smaller distance. Maranatha, your name came up. She not here? Okay then. Colton.
I stick with my answer earlier. If we're looking at the ramp and lift, it allows you to apply that lift over a greater distance as opposed to directly vertical.
Okay. He said it allows you to apply force over a larger distance. And what was the reason why it allows you to do that?
Pardon?
What was the reason why?
Well, with the ramp, instead of having to go straight and vertically, it allows you to walk it up over time.
Okay, so he said with the ramp, instead of having to go the straight distance, it allows you to spread out over time. Okay, so that was his answer. It allows you to apply force over a larger distance. That is a correct answer. Allows you to apply a larger force over the same distance. Well, the force you're applying is being multiplied by a bigger force, but it's not you applying the bigger force. And allows you to apply a larger force over a smaller distance. Well, now you're applying your smaller force over a smaller distance or over a larger distance so that over there's a larger force over a smaller distance.
Dr. Wood?
Yeah.
So the first note on the slides was that simple machines allow you to use less force to accomplish work.
Yes. That is, your force applied is smaller than the force that is coming out of the machine.
Okay.
So in the case of this ramp, the force out would be overcoming the force of gravity because you're lifting up against gravity, and the force in would be the force you apply.
Yeah, in regards to the clicker question, they're using like the terminology of it, a larger amount of force kind of confused me.
Yeah, the key is it's not you applying the larger force. You're applying force to this, and you apply your maximum force, assumedly, and over there, a larger amount of work is done. Or excuse me, not a large amount of work, but a larger amount of force is applied. Okay, now on to a TEETER. A TEETER is another simple machine. It's a lever. A lever is something that deals with torques. I assume we've all played on a teeter-totter since we were little kids, mostly when we were little kids. And you learn right away that if you have a big person and a small person, you can still balance on a teeter-totter. They can still play on the teeter-totter, but what do you have to do to get a balance on the teeter-totter? If you have a heavy person and a light person. Okay, the lighter person needs to be farther away from the point that it's pivoting, which we call the fulcrum. The heavier person has to be closer to that pivot point. And the reason for this is that a lever is dealing with torques. Now, you might have heard, I forgot who's the person who's supposed to have said this, but Give me a long enough lever, an appropriate fulcrum, and I can move the earth. Because you are, with a simple machine, multiplying the force, and would be able to apply an enormously large force if you had a long enough lever. The reason we don't use little electronic balances in this class is because our triple beam balances are an application of a lever. When you're using those, you're using a simple machine, and then after you learn how a simple machine works, you can look at it and it's clearer the physics that's going on with that triple beam balance. So that's why we don't use the little electronic ones. So if we look at a teeter-totter, here's my teeter-totter. I have to have a fulcrum. Now let's make life easy and assume that our fulcrum is at the center of mass of the teeter-totter. We can treat the teeter-totter as if all of its mass is acting at the center of mass. So I'm just going to put the force of gravity on the teeter-totter is right there. And then I'm going to have two people sitting on it. And what you told me was I need my heavier person to sit closer. So I'm putting my adult here, and the lighter person will sit farther. So I'm going to put a little child sitting here. Okay, that's the best of my drawing abilities. What will the condition be for them to be balanced? This goes back to what you've just finished, because when they're in equilibrium, they're balanced. What were our conditions for equilibrium? Now, we had two conditions. Some of the forces equal 0, and some of the torques equal 0. And for the teeter-totter, we're going to focus on the torques. Both of them still have to be true, but we're going to focus on the torques. And so I'm going to sum the torques. And remember, when you sum the torques, you always sum about a specific location. I need to look at my forces before I determine what location. So let's right now finish out drawing the forces on this. I put the force of gravity. What other forces are acting? Normal force. Where's the normal force acting? Because it's at the fulcrum, right? So I have my force normal right here, and it's pointing up directly out of the fulcrum, directly into the teeter-totter. What other forces? Okay, the weights of both people. So I'm going to have the force of gravity of the adult and the force of gravity of the child. So if I want to find the relationship between the positions of the child and adult and the forces of the child and adult, where's the most convenient place to sum my torques? The fulcrum. Why is the fulcrum more convenient?
Because then you can ignore the force in the middle.
I can ignore both the force of gravity from the teeter-totter and the force normal. So I was able to avoid 2 of the 4 forces by choosing to sum my torques at the fulcrum. So I'll do the sum of the torques about the fulcrum. And because this is a problem that everything is in the horizontal, well, everything is in the plane of the screen, then I'm actually summing the torques about the direction that's perpendicular to the screen. So I'm summing the torques about the direction coming out of the screen. And so we call it positive if it comes out of the screen, negative if it goes into it. So now we look at this, and let's take the adult first. What is the equation for torque? Torque is, okay, it's, if you want to be technical, it's radius vector crossed with the force vector. The magnitude is radius times force times sine of the angle between the two. So I'm going to have the radius for the adult, which is going from the fulcrum where I'm summing the torques out to where the adult is sitting. And then I have the force of gravity on the adult. What's the angle between that radius and that force of gravity? Okay, in the picture here, it's 90 degrees. If the teeter-totter tips, it'll change though, right? So I'm going to go ahead and say times sine of, and I will just call it theta right now, where theta is whatever that angle is between the two. So I'll just put theta here, because that angle will change. And I don't want to just have an answer for one position. Now, is that a positive or a negative torque? Positive. How'd you get that? Use your right hand rule, wrap your fingers the way it would rotate and it comes out. That is the counterclockwise. Or take your index finger and point it parallel to the radius, which is going to be to your left. Orient your hands so your middle fingers point the direction the force is down. Your thumb comes out, so positive. Okay, then we have for the child, race for the child goes like this. Is that going to be a positive or a negative torque? It's negative. Once again, you could use either of those rules, either the three. Clockwise is negative. Right hand rule, it would make it rotate so that my thumb points in, or R going this way, force going down, goes in. So I can have minus race the child, force gravity child, and then I have sine of the angle between them. That angle would be the same angle as the other one I defined as theta. Now, some people might say, wait a stinking minute. On this side, on the left side, I did the angle that was, going from the vector down to the force. The other side, it's on the other side of my lines. Well, here's a beautiful thing. Sine of theta is symmetrical about 90 degrees. So even if this was not the right angle, I'd still get the right answer because it's symmetrical. Sine of 89 is the same as sine of 91. For equilibrium, that has to equal 0. And notice the first thing that's going to happen is I can cancel out the sine theta. I wanted to put it in so we could see that it doesn't matter if you're tilted or if you're level, it's still the same positions to be balanced. And so just solving this, the easiest way to solve it is the ratio. Radius of adult over radius of child is equal to force of gravity of the child or force of gravity of the adult equals mass of the child over mass of the adult. Notice there was times G over G, but the G over G cancels. And so the ratio of distances is just equal to the inverse ratio of masses. So the one with the bigger mass has to be closer. The one with the smaller mass has to be farther. And so this is using physics. Well, actually, let's go out here. Using physics to divine where you need to sit to balance on the teeter-totter. Now, we use physics a lot in life, but we often don't think about it. How many people have ever sat down and calculated where you needed to sit to balance with your niece or nephew on a teeter-totter? Yeah, none of us do. We don't sit and calculate that. But we can explain it and show what the positions need to be from using physics. Okay, another clicker question. Which equilibrium condition is necessary to explain how a lever works, or a lever works? Which, of course, I used to say lever. TIS open for answering. All right. Let the last few come in here. Okay, and this time, my zeros are all looking bad today. The question will go to Christian Cabrera. Christian, what did you answer and what was your reasoning here? Go ahead. The sound was just turned on.
I put E, but I kind of guessed. I was thinking B or C. So.
Okay. Now that actually makes some reasonable sense there. It makes reasonable sense because we had two conditions for our simple machines. We had some of the forces 0 or some of the torques is 0. The answer is only one of those two. The energy and work ones, those are not the answer. But we had one of those two, and everyone answered one of those two except for 3 people. The torques is the one that we just used here. It was balancing the torques that allowed us to find the condition for equilibrium. So if I'm using a lever to do something like move a heavy rock, or in a case I had to use a practical case in my backyard to take out some rods, some fence posts, I put my rod like this, I put a fulcrum here, and then I'm going to apply a force here, and I'm going to have a force lifting here, and that force lifting is going to relate to the force applied through this relationship that we found by using the balancing of the torques. Okay, the last of the simple machines we're going to look at is the pulley system. Now, the pulley system is, I think, a little more complicated to think about and yet simpler actually to do the calculations. The pulley system, I have a few different arrangements of pulleys here. Let's take the first one. I pull with a tension T. If I have ideal pulleys, the pulleys have no friction, they don't change the tension, they have no mass, they only change the direction of the cable. And so then the rope comes down around the first, comes up and ties to the second. If I look at the forces that are acting on the lower pulley, remember there's no mass to this pulley ideally, what's the total upward force acting on the pulley? 2 times the tension. How much force did I put in? 1 T. Hence, I have what we call a mechanical advantage of 2 because the force out is 2 times the force in. So if we look at the next one, all you really need to do is put a line there and say, how many ropes cross that line? 3 do. That means I have an upward force of 3 tension and a mechanical advantage of 3. So if we look at this case here, of course, in this case, I'm pulling up on this, so my force applied is like this. How many times is the rope cutting there? How many ropes? How many ropes is the line cutting? It's cutting 4, and so you have a mechanical advantage of 4. Pretty simple to calculate, isn't it? Because you just have multiple ropes, all with the same tension, pulling up. Yet another clicker question, which you can answer starting now. Which equilibrium condition is necessary to explain how a pulley system works? Okay. We've got a good group here. 3, 39, 4, and 7. Okay, we're going to go to Branislav to explain why he came up with this answer. I didn't actually explain it super carefully, so I want to hear his explanation.
Well, what's wrong, right?
Yeah, the correct answer is B, but go ahead and give your reasoning.
forces involved. Machines, and so I just put it in as cool mass network, the same thing as the one before.
Okay. Thank you for answering. The correct answer here is forces, because even though I didn't really explain much about the forces, it came down to looking at the tensions. I was just looking at, I'm putting a force in that becomes the tension in the rope, and then that tension is acting on the pulleys, and I just look at how much the total force caused by tension on the pulley was, and divide it by the force that I put in, one tension. And so it was really tensions I was adding up, but in the practical sense, I was just counting ropes. All right. Now we get into angular motion. I always take longer to get into the new topic than I thought I would. That's the way teaching goes. So back to rotational motion. We've already started some rotational motion. We introduced rotational motion so we could talk about centripetal acceleration. Now, with rotational motion, it's kind of timely to note that right now there is a hurricane, Matthew, that is cruising up the eastern coastline. It probably is, getting out of Florida about now. What direction does that rotate? Okay, it actually is counterclockwise, but that was mostly a memory question. I wasn't super concerned about you getting that part right. But then the question is, what makes it rotate? Ferris? Coriolis, yeah. Okay. I didn't hear him carefully. It's the Coriolis effect. Because we have, I believe what drives this is the hot ocean water causes hot air to rise, and so air rushes in. And so air rushes in all directions. And that Coriolis effect causes air that's moving away from the equator to start to deviate in the direction the Earth is rotating, because the ground's not going as fast to the east as the air is. Air that's going toward the equator deviates the other way. And so we have that air rushing in to replace the air that rose, that goes around the circle, giving us that counterclockwise direction. And if instead of being in the northern hemisphere, it's in the southern hemisphere, everything's going the opposite direction, because instead of going north to get away from the equator, you're going south to get away from the equator. So the Coriolis effect plays a really big role in these hurricanes. That was a rotational effect. That's why I brought it up today. And of course, it's timely in the weather. So just reviewing what we previously learned, we measure angle for solid things that are rotating. And that angle relates to the arc length S. So if I have here an arc length S, then the angle made between these two lines is equal to that arc length divided by the radius. What units for angle do I have to use in that equation? I have to use radians in that equation. If I use something else, I need a conversion factor. What are the technical units of radians? What does that technically mean? Yeah, there's no unit actually there, but it's to let us know, yes, this is using the unitless value for angle. Anything else, degrees, I put later on a clicker question, gradients. Those are conversion factors. Now we talk about the angular velocity that's defined the same as linear velocity. Linear velocity is the change in displacement divided by the change in time, or the speed, change in distance over change in time. Angular velocity is change in angle over change in time. Now that we've learned the right-hand rule, we can learn that there are directions here. This really is a vector equation. I've got to kind of break it there because the directions are going to have a different rule when you put the vector signs in. But the angle is measured, once again, using the right-hand rule. If it is a counterclockwise angle, then that's positive. If it's a clockwise, it's negative. And we do have 3 dimensions of rotation. So in something like a spacecraft, the International Space Station, they talk about, the roll and the yaw and these things that just are correlating to the angular velocity in different directions. So it has directions to it, but those directions, well, if you think about it, if something's going around a circle, how do you define the direction that it's going? The velocity is constantly changing as it's going around a circle, right? But we have a constant angular speed, which we like to translate into a constant angular velocity. And the only direction that would be constant for something going around a circle is the direction that's always perpendicular to it. There are two directions always perpendicular to something going in a circle, coming directly out of the circle or going directly down. And that's where we use the right-hand rule to determine which one we're going to use by convention. Because angle is the arc length over the radius, and we have something rotating at constant radius, it turns out that the angular velocity is just the tangential velocity divided by radius. Now, I was talking to Colton before class, and the ideas of the tangential direction and the radial direction were not really clear. So if I have something going in a circle, so it's just going like this, at any location, the tangential direction is the direction of the velocity at that location. So if this thing's going around a circle, what's the direction of the velocity where my blue dot is? Okay, it's always perpendicular to the radius, and I try to choose a point where it would be up. So that's the tangential direction. Now the radial direction is the direction technically away from the center, although sometimes we use radial to mean toward the center. But the radial direction is the direction away from the center. And so, as I believe it was Jordan said, there's always a 90-degree angle between the tangential direction and the radial direction. And when we're talking about these angular variables like the angular velocity omega, next slide, angular acceleration alpha, those are only dealing with the tangential components of velocity. So angular velocity relates to how fast it's going around a circle, not to how fast it's moving toward the center or moving out. That would be the radial velocity. So get to the acceleration. If I have something going in a circle, so constant radius, and speeding up, then it has to have an acceleration in the tangential direction. And once again, since alpha is defined exactly the same as acceleration, the angular acceleration is the change in angular velocity. Once again, I have to break if I put the vector signs over time. Then using that angular velocity is the tangential velocity divided by radius, I find that the angular acceleration has a magnitude of the tangential acceleration divided by radius. Or to summarize, theta is equal to arc length over radius. Omega is v tangential over radius. And alpha is equal to a tangential over radius, where these are angular position, velocity, and acceleration. And these are linear, that is S, V, and A, position. I should put speed, but I'm putting velocity and acceleration. So relating the tangential position, speed, and acceleration to the rotational speed, well, position, speed, and acceleration is very simple. It's just divide by radius. Now, we did have this equation here, we've already learned, for the acceleration toward the center necessary for something to stay in a circle. So that is a radial component of acceleration. The centripetal is going not outward radial, but inward anti-radial, if you will. And so that depended on the speed or the angular velocity. Because of time, well, these are our kinematic equations that we start with. And if you just do the substitutions, so I've just substituted the relationship between x and theta, between v tangential and omega, and A tangential and alpha, you get a kinematic equation that looks exactly the same, just changing your variable from the linear one to the rotational one. And we'll end with this clicker question. I'm actually not going to ask somebody for the answer because of time, so you just go ahead and answer and go. Although I will explain nonetheless. Here's the answers we had. The correct answer was A, that the components of linear motion are related to the components of rotational motion are just the tangential parts. Right? It was the angle had to do with the arc length, which was tangential motion. The tangential velocity had to do with angular speed. The tangential acceleration had to do with angular acceleration. Okay, let's have a good weekend. You have a good weekend.